Okay. So good morning and happy Friday, happy Monday to everyone. It's not Friday yet. Let's see what we're going to do today. So today we're going to work more on inner product spaces, and there's something that I would like to emphasize here, that we look at inner product spaces and we realize that Rn has a very natural inner product. So one might think and wonder why we didn't get started with inner product spaces right from the get-go. And the structure was already there, in other words. And I promise you from the very beginning that our main concentration in this course would be Rn. So since Rn has such a naturally given inner product, which is pretty much the dot product of Calc 3, and so we can measure magnitudes. We can do so many convenient things. We have so many convenient tools that we had in Calc 3. Why didn't we do that from the very beginning? And the answer is that it's important to understand what structures depend on what. And pretty much everything that we have done so far depended just on the linear structure, meaning just on the presence of addition and scalar multiplication. There was something that changed in the process. So can anybody tell me, from all of the things that we have done so far, is there anything that really depends on the set of numbers we work with? Meaning we have pretty much worked with real numbers so far, and that is going to change pretty soon. Is there any aspect of what we have done so far that depends upon real numbers, upon the fact that we are working with real numbers? Is there any? The answer I'm looking for is the eigenvalues. Okay, so the eigenvalues are the roots of the characteristic polynomial. So when you have a polynomial and you try to find its roots, and you have a certain restriction on where you should be working, and that restriction is that you should be working with real numbers, or you can work with complex numbers, or any of that type, then it obviously changes the things that you can do when you move from a set of numbers to a different, from a certain set of numbers to a different set of numbers. So in any case, let's stay with the inner product today, and let's see what else we can do. So we're going to look at the orthogonal complement of a subspace. We're going to look at the projection, orthogonal projection onto a subspace. And finally, we're going to look at orthogonal matrices, which are really miraculous, wonderful matrices, orthogonal matrices. Okay, so a lot of exciting things today. And like I said, in some sense, you look at these things and you start wondering, well, why did all this nice structure have to wait for so long? But that's how things work. So in any case, so let's suppose that V is an inner product space, and I'm writing it this way so that I can remind you what I mean by this. So I could have said let's work in Rn, but what I mean by this, let me remind you, is that V is a vector space and it's equipped with an inner product. Okay, so we suppose that we have this kind of situation, and U is a subspace of V, and let U be a subspace of V. So that's a subset of V that is a vector space on its own. That's what a subspace is, right? And then we define the orthogonal complement of U by the equation that it's all W's in V that are orthogonal to every vector in U. So what do I mean by this? It's a good idea to give some geometric pictures of everything involved here. So for example, go to R2. So here's R2, right? So let's say that V is R2. What is the most routine kind of subspace that you can have in R2? Just a straight line through the origin, right? So imagine that this is U. So V is R2. Then what is the orthogonal complement? The orthogonal complement will be the set of all vectors that are perpendicular to U. And so this is going to be the complement of U. Okay, all vectors. So here I'm identifying points with vectors pretty much. And if we want to see another take on the same theme, then let's go to 3 dimensions. So now V is R3. And let's take as our subspace a plane through the origin. So this is a plane that goes through the origin. So this is U. And let's ask ourselves what is going to be the orthogonal complement of U. And the answer is it's the straight line that goes through the origin and is perpendicular to U. So this is going to be the complement of U, the orthogonal complement. And it's not a coincidence, it's actually a general fact that you can see that the dimension of a subspace plus the dimension of its orthogonal complement will always add up to the dimension of the ambient space, the space that contains the two things in it. Okay, so that's a given. Okay. Any questions so far? And this is where we have some truly wonderful kinds of exercises, of examples that can become typical exercises in this context, which are to find the orthogonal complement of a given space. So first of all, ask yourselves, if you have a vector space, Rn, let's say, Rn, let's work in R3, okay, to make our life easy. Can anybody tell me, somebody asks you to give a subspace. I really claim that there are 2 typical ways of giving a subspace of a vector space of R3 in this case. So what are the typical ways of giving a subspace in R3? And, by more generally in Rn. So can anybody tell me what are the typical ways of giving such a subspace? So you have R3 and somebody tells you, okay, give me a subspace of R3. How are you going to give a subspace of R3? a basis. Very, very good. So let me say in general, by giving the coordinates of a basis. And you know what? Let me say more generally, allow me to say a set of generators, without necessarily being a basis. Of course, optimally, you want to have a basis. I agree completely, 100%. But let's say, allow me to say just a set of generators. A set of generators. Or a basis. I mean, optimally you want to have a basis, but let's say that somebody tells you, gives you a set of generators, and they leave it up to you to find a basis if you want a basis. That's one way. Can anybody tell me another way? There's another standard way to give a subspace. There's another standard way, which has to do more with more tangible objects than abstract theory of vector spaces. This is the answer that had to do more with how we treat vector spaces abstractly, but I claim that there is another way that has to do with a more general theory that goes beyond vector spaces. And here I'm looking for a system of a homogeneous system, a system of linear homogeneous equations. So, for example, you could tell me, oh, you want know what I want the subspace x minus 3y is equal to 0. X minus 3y, okay, we're in Z, in R3, right? Plus Z is equal to 0. So, something like this, here I'm giving you one equation. I could have given you two equations. In fact, when you look at this from the point of view of linear maps, this corresponds to image of a linear map. And this corresponds to kernel of a linear map. Okay, so I would like for each of these two generic cases to find the orthogonal complement. So we wish to find the orthogonal complement and you know what? Since we're working with inner product, remember, whenever I'm asking you to find the subspace, I usually ask you to find the basis, right? So now that we're working with the inner product, I will insist that that basis is orthonormal. So I'm asking you to take one extra step, the step of using the Gram-Schmidt method. So let's do the two generic examples that are going to form the backbone of what we're doing. So the first example, find an orthonormal basis for the subspace of R3 spanned by the vector 1, 1, 1. Okay, so we wish to find an orthonormal basis. Okay, so how do we find an orthonormal basis? So I'm sorry, for the orthogonal complement. Sorry, for the orthogonal complement of the subspace of R3 generated by spanned by 1, 1, 1. Okay, so the first thing that we need to do is define that orthogonal complement. So let U be the subspace spanned by 1, 1, 1. So what does that mean? All multiples of 1, 1, 1. Then the complement is by definition all the vectors x, y, z that are orthogonal to every generator. Here, fortunately, we have just one generator. So we have just one equation. If we had 2 generators, that would be 2 equations. If we had 3 generators, that would have been 3 equations, and so on and so forth. So x, y, z, such that the inner product of x, y, z with a generator 1, 1, 1 is equal to 0. Okay. And now what is the inner product of x, y, z with 1, 1, 1? The standard inner product. This is x plus y plus z is equal to 0. So all we have to do is solve the equation x plus y plus z is equal to 0. Think of it as a subspace and find an orthonormal basis. Of course, always you need to find the a basis and then turn it into orthonormal by using Gram-Schmidt. Okay, so how do we solve this? So first of all, somebody might say, write down a matrix, right? The matrix here is the simplest possible you can imagine. And it's already in row echelon form. So you're not really gaining anything other than the inside of what is going to be a free unknown. And your only pivotal here is this, which means that this is going to be free and this is going to be free. You see how the theory sometimes tells us how to do things the right way. Okay, that's why I insist on understanding the theory, because the theory makes everything conceptual to us and saves us the trouble of having to think of things from scratch. So, I'm going back to my equation. So the matrix didn't need any work. And I express this as x is equal to minus y minus z. So now when I write down my vectors, what do I get? I get minus y minus z and y comma z. Can anybody tell me? So these are the vectors on the orthogonal complement. So these are the vectors that comprise the orthogonal complement. Can anybody now tell me what do I do? How do I find the basis for the vector, for the subspace consisting of these vectors? What do we do here? It's pretty standard. We've done it exactly. Separate y and z. Great. So this is going to be minus y comma 0 plus negative z comma 0 comma z, right? Which is y times negative 1, 1, 0 plus z times negative 1, 0, 1. In the past, we would have stopped here and say, okay, here's the basis. That's all you wanted. Goodbye. But now, so these two vectors form a basis. Again, I remind you, they're linearly independent because there are 2 of them and one has a 0 where the other does not. That's how you know that they form a basis, right? So, however, we want to make it into an orthonormal basis. And for that reason, we're going to use Gram-Schmidt. So what I want to do now is Gram-Schmidt on the vectors 1, negative 1, 0, and Actually, it was the other way around. It was -1. Yeah, I need to go myself back to the previous slide because, as you can see, I don't remember the vector. So I will do this. And -1, 0, 1. Okay, so I want to do Gram-Schmidt on these two vectors. Okay. So here's the previous slide. And okay, so let's do our Gram-Schmidt. So what do? We normalize the first vector. Is there any simplifying step before we normalize? No, this vector is as simple as they come, right? What is its magnitude? Anybody? What is the magnitude of the first vector? Magnitude of first vector. Okay, that's the attendance for today. Magnitude of the first vector. Everybody send me this. See, everybody knows how to find it, but send me the magnitude of the first vector. Okay, so I guess we all got it right. So I divide by that magnitude. And we have -1 over square root of 2, 1 over square root of 2, 0. Okay, so that will be the first vector. And now for the second vector, what do? We take the second vector. That's the Gram-Schmidt method. Was that reaction fast enough? Borderline. Borderline. Please attend the lecture. Oh my gosh, there's so many people who have the lecture on the back burner. Oh, How nicer would life be if people did really trust somebody who tells them, please attend the lecture? Much nicer. Rather than, no, I'm going to do my own thing here. You don't know what you're talking about. What can we do? What can we do? Not too much. The nice thing I should be happy about is that the people who responded to the question were more than the ones who didn't respond, who responded late. So you can have it all, I guess. No, I saw somebody leave it right away. We took attendance. That's it for me. That does it for me. Anyhow, let me go back. I'm just a grumpy old man. So what do we get? We get 1 over square root of 2. And then that's the inner product, right? And then we have -1 over square root of 2, 1 over square root of 2, 0. And then this will become a -1, 0, 1, minus, and here we will have -1/2, 1/2, 0. And when we take that difference, this will give us, yeah, sure, but what step? I took the inner product here. I think this is maybe the step that needs explanation. When you take the inner product, you multiply this with that, then this with that, this with that, and you add them together. That's what the inner product in R3 is. So that number, this whole mess, was 1 over square root of 2. Okay? And then I multiplied 1 over square root of 2 times 1 over square root of 2, and that's 1/2. That's what square root of 2 times square root of 2 is. It's 2. Right? I hope that explains it. And this will give you -1/2. -1/2. Another -1/2. And it also gives you 1. Right? So that's the vector. And remember, this is the situation where you might as well simplify it before normalizing. How do you simplify this? Just factor out 1/2. If you factor out 1/2, you're staying with -1, -1, 2. Okay, so that's the vector that I'm going to normalize. So Let's write it so that you can have it in writing. Sometimes when we write things and we get used to them much better. So instead of normalizing -1/2, -1/2, 1, we are normalizing its positive multiple, scalar multiple, -1, -1, 2. The magnitude of this is square root of 6. And so it's going to be -1 over square root of 6, -1 over square root of 6, 2 over square root of 6. And finally, that's it. So what are your two, the orthonormal bases? This is the first vector. This is the second vector. That's it. We gave the orthonormal basis that we were looking for. Okay? Questions? Questions? Let's do the second case now, the case where the vector space is given, the subspace is given by a system of equations. Okay, and that is really fun. That's the kind of problem that I like. And let me show you why. Let me show you why. So find. So here's how the problem will be given. So find an orthonormal basis for the orthogonal complement of the subspace U is equal to XYZ such that X minus Y is equal to X plus Y is equal to 0. Okay, here's the previous slide as you asked for it. And now, this is there is something really cool about this. You might think to yourselves, oh, so are we going to find the basis? I mean, how are we going to do this? And this has a really wonderful way to treat this. Here's the idea. Here's the idea. It's one of those wonderful ideas. Every linear equation can be thought of as an inner product equation. Every time you see a linear equation, you can always think of it as an equation giving you the inner product of a vector with some generic vector xyz being equal to 0. Okay, why? Why? Let's see why. So here's what I'm going to say. I'm going to say that this subspace is also the same thing as the inner product of vector x, y, z with the vector 1, 1, 0 being equal to 0. So your equation can simply be interpreted as an equation in the inner product, okay, involving the inner product. Which means, which tells you right away what? So U is, So U is the orthogonal complement. So every subspace which is given to you through homogeneous equations is actually given to you as an orthogonal complement. It's just that we didn't realize that before. So U is the orthogonal complement of the subspace spanned by the vector 1, 1, 0. Call this subspace V. Just for the sake of the argument, you will see why. Because I wanted to tell you that U is the orthogonal complement of V. So when you ask me what is the orthogonal complement of U, that is twice the orthogonal complement of V. But the orthogonal complement of the orthogonal complement, can you guess what that would be? The orthogonal complement of the orthogonal complement of a subspace. It's the initial subspace. It's the subspace itself. Okay, so that tells you that so the orthogonal complement of U is spanned by 1, 1, 0. And so to find an orthonormal basis, all you need to do is normalize this, which is a 6th grade exercise. And its orthonormal basis is simply given by 1 over square root of 2, 1 over square root of 2, 0. And that's it. So this is really an exercise on understanding things. There's not too much work to do here in this particular problem. We need to understand what it is that we're doing. Questions, please. Questions? Okay, then. So now I would like to explain what is the orthogonal projection. What is the orthogonal projection? And this is understood better if we give vectors in terms of arrows, actually. So let's work in R2. So in general, you can always think for all intents and purposes of vectors as being arrows or identify them with their endpoint. But basically, if this is the vector space V, so the whole thing, and this is the subspace U, then projecting a vector onto U means simply to take this vector right here. So this is what I'm going to call, so let's say this was the vector V. So this is going the projection with subscript U of V. So this is the projection of the vector V onto U. It's really the vector with which the vector, it can be defined as the vector in U, in uppercase U, that has the smallest distance from the vector V. So the distance, meaning the norm of the difference of the vector V minus its projection, is the smallest possible among all distances V minus U for U in U. And that's a crucial thing that is being used very regularly in the process of approximation. So this is something that we're going to use next time in a very, very powerful way. So not only that, but also the difference V minus the projection is orthogonal to U. So I think the best picture, let me magnify a little the picture that I drew here. So this is the vector U, right? This is the subspace. I'm sorry, this is the vector V without an arrow. This is the vector V. This is the subspace U. I'm sorry, let me catch this question. There is a question. This is a subspace. In my picture, and that's one of the reasons that it's you have to always take those pictures depicting spaces and subspaces with a grain of salt, is represented as an infinite line, right? So it doesn't go, it continues indefinitely, right? So so this is the projection onto the subspace U of V, and this is V minus again, V is not a vector. V is not a vector. V is a subspace. V is a subspace. We're projecting onto a subspace, and that's so this subspace could be a two-dimensional subspace or a three-dimensional or a 10-dimensional subspace. We're not projecting onto a vector. Okay, and this is the difference, V minus the projection onto U of V. And you can see that it's, or you can also see it right here. So this is the same thing, V minus the projection onto U of V. So in other words, the vector V is written as its projection onto V plus V minus that projection. And this is a vector that belongs to V. And this is orthogonal to V. So this is a vector belonging to the orthogonal complement of V. And this is the unique way that a vector, I'm sorry, I'm saying V and I mean subspace U, sorry about this. And this is the only way that you can write V as a sum of two vectors, one which belongs to U and one which is orthogonal to U. So that's pretty much the definition of the projection. If you use any other vector in U, you're not going to get orthogonality. So What is the formula? The formula is especially simple. So it turns out that if U1 up to UK is an orthonormal basis for U, then here's the formula. The projection onto U of V is the inner product of the first vector of V with the first vector times U1 plus all the way to the last one. So let's give an example of how this formula works. Let's give an example. So find you know what? I bet. I mean, I'm sorry. Yeah, I could have used N, or any other letter would have been fine. I know I usually use N, so I beg your pardon. I didn't mean to confuse anyone. Okay, I mean, please understand that N is as generic to use as any other letter. So find a formula for the projection. Let me give you something which is as close to the homework problem as possible. So find the formula for the projection of onto the subspace. And here, when I say projection, I should sometimes people like to say, to emphasize and say orthogonal projection, because one can say, yes, there are other kinds of projection, but here we mean orthogonal projections onto the subspace of R3 spanned by one, 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 and 1, 0, 0. Okay, so what do we do here? Remember that the formula that I gave you says that we need an orthonormal basis. And here we just have a basis. This is obviously not orthonormal. These vectors are not, I mean, the first vector is not a unit vector. So what do we need to do? First step, how do we make it orthonormal? How do we make this orthonormal? Gram-Schmidt, of course, Gram-Schmidt. Okay, so I normalize the first vector. Be careful, you cannot just divide by the magnitudes and say that you made it orthonormal. You just normalize the vectors. You need to make them orthogonal too, and this is where you need Gram-Schmidt. Okay, so 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And so that's the first vector. And for the second vector, we're going to do 1, 0, 0 minus the inner product of the first vector with of the second vector with the first vector that we just found. Here, there's a remark that has to be made. If you were to apply the Gram-Schmidt method in the basis that you get by reversing the order of these two vectors, the work would have been so much easier, so much simpler. Okay. So, but that's all we need to do here. And what do we get? We get 1, 0, 0 minus Here we get 1 over square root of 3. That's the inner product. And you have 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. This is the reason why I chose the vectors in this order, so as to do another example of Gram-Schmidt. So 1, 0, 0, minus 1/3, 1/3, 1/3, which is 2/3 minus 1/3 minus 1/3. And of course, how do I normalize this? I'm not going to normalize this vector. I'm going to normalize 1/3 times. So I'm going to factor out the 1/3 to make my life simpler. I'm going to normalize this vector. And this, of course, has norm square root of 6, which means that I'm going to get 2 over square root of 6, negative 1 over square root of 6, negative 1 over square root of 6. Right? So here's my base. I'm not done. I just got the orthonormal basis. Now I need to apply this formula. So how do I apply this formula? So I'm gonna do the projection onto U of the vector x, y, z is going to be the inner product of x, y, z with the first vector, which was what? It was 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, times the vector, should not forget my t's, times the vector 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, plus the inner product of x, y, z with the second vector, which was what? It was 2 over square root of 6, negative 1 over square root of 6, negative 1 over square root of 6, times this vector. Okay, so there's a little bit of algebra to be done here. Nothing too much. And let's carry this out. So the first inner product will be what? X over square root of 3 plus y over square root of 3 plus z over square root of 3 times 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 plus 2x over square root of 6. Sorry, no comma here. This is a number. The inner product is a number, of course. Minus y over square root of 6 minus z over square root of 6 times the vector 2 over square root of 6, negative 1 over square root of 6, negative 1 over square root of 6. I'm doing the scalar multiplication here, and I get x plus y plus z over 3, x plus y plus z over 3, x plus y plus z over 3, plus, and here I will get 4 on the first coordinate. What do I get? I get 4x minus 2y minus 2z over 6, and then 2x plus, I'm sorry, minus 2x plus y plus z over 6, and minus 2x plus y plus z over 6. Add them together. So to make our life easier, this is the same thing as 2x minus y minus z over 3, right? So when I add 2x plus y plus z over 3, what do I find? I find 3x over 3, right? The other two things cancel. Then the second one, I need to make it 2x plus 2y plus 2z over 6. And this will give me 3y plus 3z over 6. And the same thing I get on the last coordinate. There's some very interesting algebra going on here. And the final answer is x, comma, y plus z over 2 y plus z over 2. Very nice algebra. Okay, and that's the formula for the projection. No, I got the over 6 when I multiplied, so let's make sure that you follow what I did. This gives me this, right? And this gives me that. Okay, just to make sure that we're interpreting it the right way. Okay. Any more questions? Okay, so that's the formula for the projection. So it has a good amount of algebra. Let's take a 5-minute break and make that 7-minute break, and then we'll talk about orthogonal matrices. Okay, so let's start our recording again. Are there any questions on the work that we did in the previous hour? Yeah, sure. Here is the last slide. Okay, so let's start talking about orthogonal matrices. So, oops, is there a question that I missed? In the last question, I didn't write the orthogonal complement at all. In this question, no, in this question, there was nothing. The last time was here. Is this the one you're asking about? Yeah, so pretty much what I said is that U is the orthogonal complement of the subspace spanned by 1, which means that the orthogonal complement of U, which is what we really want because it said find the orthogonal complement of the subspace, is the orthogonal complement with the orthogonal complement, which is the original subspace. That's pretty much what I'm saying. So let's talk about orthogonal matrices now. An orthogonal matrix is such a wonderful matrix. Okay, what are the properties that it has? So an n by n matrix is called orthogonal if and only if only one of the following equivalent conditions. So what I mean by equivalent conditions is that if one of them is satisfied, then all of them are satisfied. If one of the equivalent conditions of the following equivalent conditions is satisfied. First of all, the product of the matrix with its transpose is the identity matrix. The inverse matrix of the matrix is its transpose. The rows form an orthonormal basis of Rn. The columns form an orthonormal basis of Rn. It doesn't get any better than that, right? You have a matrix that has all these wonderful properties. And like I told you, whenever you check with whether something is an orthogonal matrix or not, it needs to have just one of these properties. If it has one, then it has everything else. You don't have to check all of them. You have to check just one of them. But it will be very useful for us to use whichever property seems most convenient. So, so if I wanted to give you an example of an orthonormal matrix, obviously the identity matrix orthonormal, okay, that's not such a great example. But I'm sorry, an orthogonal matrix, but also if you take the columns the other way around, so that's in general a feature of an orthogonal matrix, that you can mix the rows and the columns any way you like, and you still get something which is orthonormal, which is orthogonal. So these two matrices are orthogonal. And then I can write down my favorite basis, which is 1 over square root of 2 negative 1 over square root of 2, and 1 over square root of 2 1 over square root of 2. So these are orthonormal. So all of these are examples of orthogonal matrices. And then if you look at other examples that we already saw, I think what I'm thinking of a 3 by 3, other than the obvious examples that have the standard basis vectors. So I'm thinking of 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And then what do we have? What did we have here? 1 over square root of 2 negative 1 over square root of 2 comma 0. I can't remember the third vector, right? But here's the coolest thing in the world. Okay, I claim that it's easy to find it. So I'm going to put question marks here. And I'm going to ask the following question, which will be one of the questions that we will be asking in this context. If somebody gives you 2 out of the 3 columns of an orthogonal matrix, can you find the third one? First of all, let me put it this way. There will always be 2 options for the last column, because you could take a vector and you could take it the opposite vector and you would still get an orthonormal basis. So there will be 2 options, but any of the 2 options is going to be just fine. So the question is, how can you find this? And the answer is very, very nice. Look, here's how I'm going to do it. Okay, so first of all, start with a number that you have to put right here. Let's start with this number. Let's start with this number. Okay, who do you know? Remember that in an orthogonal matrix, not only the columns form an orthonormal basis, but also the rows, which means that the rows need to have magnitude 1. So that means that 1 over square root of 3 squared plus 1 over square root of 2 squared plus whatever this number is should add up to 1. That is going to pin down the number for you by very, very precisely. Because 1/3 plus 1/2 is going to be 5/6. And so the other side is going to be 1 minus 5/6 is 1/6. So that will tell you that the question mark is going to be plus or minus 1/6. Okay, so far so good. So for the moment being, I'm going to put just 1/6. I'm going to explain why in a second. I'm going to just write 1 over square root of 6, reserving the possibility that it's going to actually be minus 1 over square root of 6. But basically what I'm going to do is I'm going to find the numbers in absolute value, meaning without the signs, and eventually I'm going to figure out what the correct signs are. So for the second one, the numbers are pretty much the same. So I'm going to put another 1 over square root of 6. And for the last one, you need to have what? You need to have 1 over square root of 3 squared plus 0 squared plus whatever squared should be 1. And if you solve this, you will see that you get on the other side 2/3. So it's square root of 2 over square root of 3. And you know what? Square root of 2 over square root of 3, if you multiply, I mean, I hate to do this, but it's so much nicer if you write it as 2 over square root of 6. Okay, so it's 2 over square root of 6. Now, what I want you to understand is that the 3 numbers that I found by using the requirement that the sum of the squares of each row should be equal to 1 are the correct numbers, with the possible exception that I have to modify the signs. And now the question is, how do I choose the signs so that I get 0 inner product for all the rows? So for example, what I mean by that, for all the columns. So what I mean by that is, if you take the first column, right, take a look at the first column. It's all positive numbers. It can be right that when you multiply with, when you take the inner product with the last column, that should give you 0 inner product, right? There's no way this happens, right? Because they're all positive numbers. So you have to arrange it somehow so that you get negative numbers too. So here's the thing. I will go initially, when I check the 2, I will go with you said plus minus plus. No, it's not going to be plus minus plus. Not something automatic that you can predict. You have to look carefully and see what you have here. And this 2 should actually tell you that you should distribute the signs so that you have you balance everything, every positive and negative number, especially since the first row is all positive numbers. So since the last row, the last entry is twice the other 2, to balance things with the first column where all the numbers are equal, what I put is minus, minus, and the last number, I leave it as plus. And then you need to test and possibly do further modifications. Here, you don't need further modifications with the second column. And if you check it with the second column, you will see that the inner product is 0 right away. I mean, in the worst case scenario, the possibilities here, there are 8 possibilities, which are really 4 of them. So you could try randomly all of them till you find the one that gives you inner product equal to 0. But like I told you, the way I did it here is I looked at the first column. I saw that the numbers are all equal. And in the last column, the last number was twice the first one. So that's how I did it. And if you look at the third homework problem, you will realize that it's pretty similar to this kind of situation. Okay. Any questions? Now, one more thing that I would like to add. This is not a characterizing property. This is just a property that the determinant of an orthogonal matrix is either 1 or -1. Why? Because the determinant of the transpose is equal to the determinant. So you get that the square of the determinant should be 1, and this is possible only if 1 is if the set of all orthogonal matrices is denoted by O of n, and it's called the orthogonal group. Orthogonal group. It's a group. in the sense that the product of two orthogonal matrices is orthogonal. The product of two orthogonal matrices this is a wonderful property. And the inverse of an orthogonal matrix is orthogonal. The what do I write? The inverse of an orthogonal matrix is orthogonal. And finally, we have one subgroup of this, which is called the special orthogonal group. This is the special orthogonal group. And this is all the matrices in the orthogonal group whose determinant is equal to 1. Like I told you, the determinant of an orthogonal matrix can be either 1 or -1. If you take the ones that have determinant 1, then they form a special orthogonal group. And that's all I had for you for today. Next time, we're going to see a very exciting application of orthogonal matrices and something related to the dimension equation. For the next quiz, you know, what did you like out of all the things that we did today? Boy, I don't know. Let's leave the suspense for next time. So it's going to be one problem similar to the 3 homework problems, to one of the 3 homework problems. So obviously the fastest one is to complete a matrix and make it orthogonal, like the one we just solved. The other one is to find the projection onto a subspace. And the first one is to find an orthonormal basis for the orthogonal complement of a subspace. There we have 2 cases for the description that you may have for that matrix. So let's leave it at that. Let's leave it very interesting for next time. And yeah, but I want you to know all these 3. So for problem, so you're asking me for homework 11, the first step is to apply the Gram-Schmidt. Let me take a quick look so that I can answer the question. No, it has nothing to do with Gram-Schmidt. I'm already giving you an orthonormal basis. This is pretty much the thing that I said in the lecture about how if you apply Gram-Schmidt to this basis, you will get itself. That's the funny thing with the Gram-Schmidt. I mean, feel free to apply it. It's a ton of operations, but eventually you're going to get the same thing. Yeah, so you need to show that the norms are 1, right? And one more thing. What is the other thing that you need to show? That the norms are 1, exactly, and the inner products are 0. So there are pretty much 3 inner products that you will need to take. Show that, so the first with the second, the first with the third, and the second with the third. Show that these 3 inner products are 0. Show that the norms are 1, and you have established that it's an orthonormal basis. Okay, so no Gram-Schmidt here. But in some sense, the third problem on the homework, we solved something very similar. So you need to find first a basis for the kernel and then make it orthonormal. Yeah, okay. So we solved something very similar in class. And I think, you know what, you could, yeah, that's all. So find the basis using the method that we have seen for bases in general, and then make it orthonormal. That's all. Okay. Okay, then. Great. We have, take a look at things. We have 3 more lectures with new material. I mean, all this stuff is about 100 years old, but, you know, anyhow. you know what I understand by new, what I mean by new. Okay, and then we will review and do some applications. So that will be all for today. I wish everyone a very, very nice rest of the day. Determinant equals 1, equals 1. Yeah, that's what it says here. I'll see you on Wednesday.